This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 181 on this Pi Day, March 14th. Today's presentation is the investigation of locally generated and long-range smoke transport using aerosol measurements. I'm glad to have Kyle Eskew from the University of Oklahoma School of Meteorology with us for today's presentation, and facilitation following his presentation from Chris Schmidt, Fire Detection and Characterization Algorithm Lead and Researcher at the Cooperative Institute for Meteorological Satellite Studies, University of Wisconsin-Madison. As you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. Please post your questions in the chat and we will field them in the order they are asked. If you have not signed in with your full name, please note your full name when asking a question in the chat so we can follow up if necessary. We're always looking for future presenters. Please contact our Tower S team, Kashad Bowman and Emily Maddox, if you would like to present. And the training team can help create training materials that may be unavailable or point you to materials you may be unaware of. Ross Van Til with OCLO can help with that. I'd like to thank our Tower S team and OCLO, Kashad, Emily, and Ross, GOZAR, JPSS, our facilitator, our presenter, and all of you for being with us today. Without further ado, let me give a little more background into Kyle, who's a junior at the University of Oklahoma School of Meteorology. He is a member of the Atmospheric Aerosols and Air Quality Laboratory, where he conducts research to understand the impact of long-range transport on the physical properties of aerosols as it relates to wildland smoke in Oklahoma. He will complete his research project at NWS Tucson this summer to continue research on wildfires, specifically the correlation between Evaporative Drought Demand Index and wildland fire growth. Kyle, welcome to the Satellite Book Club today.
All right, thank you so much for having me for the introduction. Thanks to the whole team for reaching out and see if I would present today. I greatly appreciate it. And so, as we know, wildland fires produce very large loadings of aerosols. In fact, I spent very little time in an operational NWS environment. When I started my student volunteership last summer in June, my very first day on the job was entirely governed by air quality advisories, air quality alerts. And if you're anything like us on the ops floor, you were maybe playing around with newfound HERS smoke products. Maybe they were working well, maybe you're getting frustrated with them. Whatever your experience may have been, I think we can all agree that understanding smoke, how it moves through our atmosphere, and how its physical properties changed with the amount of time it remains suspended is particularly important. And so this research seeks to understand or probes the physical properties of aerosols as they travel through our atmosphere to understand some column measurements, AOD, single scattering albedo, and how those change with time. And then also the height in our atmosphere at which they're at, depending upon the emission location, how close they are to the site in question, or if they're governed by long-range smoke transport, say the west coast of California, to those of us out here in Oklahoma. So in order to accomplish this research, we have a micropulse LiDAR at the Atmospheric Radiations Measurement Southern Great Plains site. If you're not familiar, it's in Lamont, Oklahoma, which if you see the figure in the little plot in the bottom right there, that red dot in northern Oklahoma. And from there, that LiDAR sends a signal up into our atmosphere and then a transceiver to detect backscatter, effectively telling us how intense or how much light is being scattered throughout our atmosphere. From there, since we are generally able to determine the height at which the smoke plume is in our atmosphere, we can use HYSPLIT to run a backward trajectory, usually going backward about 96 hours, although variable depending on the circumstances. Understand from where that smoke originated, how long it took to actually get to our LiDAR, and what other AERONET sites it may have passed along the way. And so those AERONET stations are the ones used in this study, also all appear as red dots on that figure in the lower right there. And so those allow us to probe the actual physical properties of our aerosol. Here we use for AOD, SSA, AEE, and AAE. And so when we're actually looking at the returns from our LiDAR plot, it's great at telling us, what is scattering light, but it doesn't actually discriminate, at least not directly, the backscatter product between what is smoke and what are other things. And so we apply a machine learning cloud masking model from Cromwell et al. 2019, which simply operates on a one cloud, zero no cloud scheme to tell us, at least give a best guess on what is cloud and what is smoke. Satellite data in particular. So the fire radiative power is a satellite-derived measurement that tells us the rate at which thermal energy is emitted from wildland fire. It's great. It's used as a proxy for how intense biomass burning is or how large a wildfire happens to be. It's a crucial aspect of Modis and Veer's thermal anomaly products. You may have seen those before. I have a couple throughout our presentation. So in this research, that helps us understand where the likely origination point of that smoke is, i.e. telling us where our fire is, and from where those smoke aerosols are actually originating from. The method used to mask clouds here uses the normalized relative backscatter and the linear depolarization radio, each in one input channel, into a machine learning model. But as you'll see on some coming slides, it's not perfect. So satellite data is great at helping us verify the accuracy of that cloud mask and kind of explaining the social impact of smoke and the actual impact. I know some members of my lab gone it and given interviews, especially last summer when air quality was significantly reduced in Oklahoma on account of smoke. And so satellite data and satellite imagery, hugely important in helping to socialize the impacts of this research. And I promise this right here is the last slide with words and not pretty pictures. But important part here is on the LiDAR plots that you'll see, is there actually a ratio of the range corrected backscatter to the attenuated or the Rayleigh attenuated backscatter profile. That attenuated profile assumes a standard atmosphere. We only use about the first 24 hours of any data set to generate that profile. It doesn't change very much, and it's very computationally expensive to keep running it over and over and over again. And so once we get those plots, that ratio is plotted logarithmically and helps tell us where we have extra scatterers in our atmosphere. And so telling us where smoke or clouds are generally, and then hopefully applying that cloud mask as described so that I'm only left with smoke to deal with in my data set. So as mentioned, applying that cloud mask with the LiDAR usually works pretty well, but you'll see one example later on in this presentation where it doesn't. So I wanted to toss this particularly extreme example in here. Of course, many times during major wildfire events, especially when it's being long-range smoke, you also have clouds at the same time. And so in this particular case, on the 14th of September here, we see this is pretty much all cloud. Everything 7 kilometers and above here is cloud. And unfortunately, for whatever reason, machine learning model didn't appropriately mask this. In fact, this really isn't that unusual of a situation. So I just have a loop from one of these major smoke events in Oklahoma. And yeah, as it goes through here, we see mix of clouds and smoke, but being able to actually verify that cloud mask is working is very important, and a critical use of satellite data here, along with the fire radiative power. All right, let's not play that again. Here we go. Okay, so actually looking at some data and results here. So when smoke is transported great distances to our LiDAR site in northern Oklahoma, it often arrives at much greater heights in the atmosphere, usually around 4 to 6 kilometers above ground level. We see in this case, lots of wildfires along the Pacific Northwest and British Columbia there. Us, at least according to HYSPLIT, getting our smoke from kind of the north side of those fire complex. And when we see when that arrives on our LiDAR plot here, So look, beginning at about 10 a.m. local time that day, there we see our smoke. It arrives just below 4 kilometers there. 3750 is what I used for that HYSPLIT. So we know it's at 3,750 meters from atmosphere. Looking back 96 hours, where else traveled. And so from there, we see our smoke arrives and it begins to descend. And so usually when we see these sorts of long range smoke transport cases, they tend to arrive in about the 4 to 6 kilometer band. In this case, because it took almost a full 96 hours from the fire to get here, to arriving a bit lower, so we notice with more time that smoke does tend to mix down. You can actually see pretty visually on the plot here quite well, and the reason I selected this case is it does begin to drop or descend through atmosphere, and really by the 18th, this remains fully suspended in the boundary layer. 0 to 2 kilometers. And in the next case, we'll look at deposition and how that tends to get removed. But the 18th, it turns out in this particular instance, it's really challenging to exactly determine where all of that smoke is originating from, particularly because on that day we started to get a good number of local fires, locally generated smoke here. And we notice with those locally generated cases, that smoke often arrives or tends to remain suspended in the boundary layer. So here we have by the 20th of September from that large smoke event, outbreak, probably not the right word, event. And we see some of it staying in the boundary layer to begin the day. And then often, or beginning right around 6 a.m.-ish local time there, we get another little streamer of smoke from some of those fires above or in the Kansas, Missouri region. And those get to our site, they remain in the atmosphere. And they tend to remain until removed by deposition or when they're kind of just ejected out of the region. And so this was kind of interesting in particular here. And this is what I point out. So this one on the left side, the 21st view of those clouds at 2 and about 5 kilometers, not getting well masked. But we kind of see here on the previous day, some of those returns start to diminish, mostly due to dry deposition, gravity forcing our aerosols to move down and settle on the surface. But then on the 22nd, we don't really see all that smoke clear up until it rains. And I notice my slides move kind of slowly and tend to bounce around there in the corner. Not sure why that is, sorry about that. But once that rain falls, then our smoke tends to be removed from the atmosphere. Some of the interesting aspects of this research is actually probing how the physical properties, or if they do, of our aerosols actually change with time. And so probably the most well-known indice is the Aerosol Optical Index, which kind of just tells us how much light or how much is being extinguished throughout our column by dust, haze, smoke, other things. And it can be used as a proxy for aerosol loading. And so if you can see on this here, 0 to 4 days, so those are all rounded. So 0 days is anything less than 12 hours, 1 day, 24 plus or minus 12 hours. And with time there, we don't actually see a particularly stark change in the actual amount of aerosols in our atmosphere, depending on if it takes 0 to 4 days to get here. So as to say, from the fires much closer that tend to get here almost immediately, whereas the smoke events where we have smoke arriving to us from California or Canada, we still observe roughly or close to the same amount of aerosols in our atmosphere. So the intensity actually isn't reduced based on the distance we are from the fire or how long it takes to get here. In addition, so SSA is single scattering albedo. It's a ratio of the scattering to extinction efficiency. Wildfire smoke tends to be in the 0.9 to 0.95 range. And here we do observe a slight decrease with time, which is a little bit of an unexpected result. And I should provide a disclaimer that a lot of these results are preliminary. We hope to look at about the 2012 to 2023 timeframe for events, but 2020 and 2021 actually do comprise close to about half of those cases. We have very good Lidar data for them. And at least looking at that data, we see a slight decrease in scattering with time, which isn't exactly what we expected, because generally you would assume your aerosol remains suspended in your atmosphere. You have the sun, it bleaches your aerosols, they become brighter and scatter a little more light. Although these results kind of suggest that may not necessarily be the case, or at least not the case always. Yeah. So looking at two more here. So our absorption angstrom exponent and our extinction angstrom exponent. So AAE is a measure of how absorption depends on what light wavelength. That pretty much doesn't vary with time at all. But looking at the extinction angstrom exponent, or how extinction depends on light wavelength, we know that to be inversely related to particle size, and that increases a little bit with time, which would suggest a marginal decrease in particle size, i.e. our aerosols get slightly smaller depending on how long they take to arrive to our LiDAR site at SGP. Here we go. What am I doing on time? Okay, pretty well. I've got about a minute here. So kind of the most important takeaways here are high-split backward trajectory analysis does closely track the movement of aerosols through our atmosphere. The caveat there is that previously we tried a method where we weren't necessarily always relying on LiDAR data, and it didn't work particularly well because we didn't know the height at which the aerosols were in our atmosphere. And without that information, you need to actually set an origination point, height, and high split. Even attempting to estimate, it didn't always work well. But when we actually have evidence for the height of the smoke, high split is pretty reliable for estimating how those smoke plumes move across the continental United States. In addition, aerosols from long-range smoke transport events arrive at much higher heights in our atmosphere than those from locally generated smoke. That is, locally generated smoke tends to stay and remain in the boundary layer until removed by deposition. Long-range smoke transport, that smoke tends to arrive much higher in our atmosphere, and it also tends to exit much quicker as long as it doesn't become suspended in the boundary layer, at which point kind of subject to some of the same considerations as the locally generated smoke. In addition, the physical properties of our aerosols don't change significantly with transport time. Aerosol optical depth, as I just explained on the previous slide, or the amount of aerosols in our atmosphere, doesn't actually vary too much depending or based on how long it takes the smoke to transport, or the distance smoke travels to get to us. And we do see a slight decrease in our particle size with aging. So I notice I've gone a minute over here, but yeah, if anyone has any questions or kind of the next phase, I'd be happy to answer them.
Thank you, Kyle, for that presentation and for showing us this interesting work. I'm encouraging all of you to stay on for the discussion. I am taking attendance, by the way, so we'll notice if you leave. Also, I'd like to specifically encourage participation from the field offices, field forecast offices, and regional HQ. And when you do put questions into the chat, please make sure your full name is specified, either in your identification or otherwise. And also, afterwards, if you could please complete the SBC presenter facilitator form that will be posted in the chat room, that would be great. Also, a week from today, on Thursday, March 21st at noon Eastern, Frank Alsheimer, Science and Operations Officer from NWS WFO Columbia, South Carolina, and Tim Schmidt, my office mate, who spells his name incorrectly, from NESDA STAR, will provide an update on the GXS instrument for GeoExo. That's the new sounder. Also, please contact the Tower S team, Kashal Bowman and Emily Maddox, for questions about SBC or for questions with configuration of satellite products. Okay, and with that, we'll start the discussion. We have a question in the chat from Brian Curran. Have you noticed layers of smoke above the PBL with time after the PBL decouples after sunset? I presume that means vary with time after the PBL decouples after sunset.
Yeah, I'd imagine. So yeah, have I noticed smoke above the PBL vary with time? I would say my answer to that is no. We see, and obviously I was only able to throw so many in our presentation here. maybe here. No, I can't say that I've noticed smoke above the PBL vary with time after sunset or when we see decoupling. Yeah, I think my answer there is just kind of no.
All right. I also neglected to mention that if you can submit your questions through the chat room or indicate otherwise that you would like to ask a question verbally. So from an air quality standpoint, why is it important to understand the time of transport, in particular, rather than simply the resultant impact? Is there other work regarding this?
Yeah, so one of the things that we noticed, or at least when I started this, is we had some other members of my group. They attempted to do this analysis, but sort of just using kind of a fixed transport time depending on where it originates from. So, say it came from, California, we'd say, on average that takes about 2 days. And so we'll kind of all toss that in a 2-day bucket. Or, this is coming from British Columbia, that tends to take about 3 days, kind of put it there. And as we undertook this research, it turns out that that is very dependent on the upper level pattern, which is pretty obvious, but it actually varies significantly. We've seen, there are some instances where there are fires in Southern California with, we get really strong directly zonal flow at the height of the smoke plume, and it can arrive here in as little as a day, which is, or other times it kind of, takes a path and kind of goes out over the Pacific and then comes back and finds its way to those of us here in Oklahoma. And that may take 4 days. And so from an air quality forecasting standpoint, trying to understand the amount of time or when the impact is actually going to occur is rather important. And the previous work doesn't always take into account the upper level pattern and how long it would actually take smoke to arrive.
Yeah, I was a little surprised actually that you don't see more of the larger material falling out, but I guess I haven't given it that much thought for those longer transports. Yeah, since I work with ghost fires, I'm obligated by law, and you can check the infrastructure law from a couple of years ago. It's in there, and trust me. I'm obligated to ask a relevant question. VIIRS and MODIS capture fires at a specific time of day, so they do miss the diurnal behavior and a decent number of shorter events. Did you have any issues with identifying the sources of your smoke plumes given that?
I did not. And a lot of that may be due to the fact that, kind of looking at a lot of the larger, more impactful smoke cases, we have a lot of instances where they're really large fire complexes where detecting those is maybe a lot easier when you get kind of the smaller, more local fires. And so, no, particularly for this data set or the stuff I was looking at, I did not observe that to be an issue.
Okay. Tim Schmidt has a question for you. Did you compare your LiDAR observations to any GOES ABI-derived level 2 products, such as Aerosol Optical Depth?
Yes, we did. We did take a little bit of a look at actually exactly Aerosol Optical Depth. In fact, that's the only one I compared it to, but I did compare it with AOD. And I will say that agrees quite well with what is shared here. Kind of actually even compared some of those AOD measurements to what we observed from our AERONET sites. And at least as far as these events go, they did verify, they did match pretty well. And so, yes, we did compare some of those level 2 products, and they did agree or verify each other quite well.
Oh, that's good to hear, although we all know that GOES products are all around excellent, so it's not a surprise. How accurate or useful is HYSPLIT in doing those back trajectories? Like, did you see any issues with using it for this work?
Yeah, so kind of computing those backward archive trajectories tends to be pretty reliable as long as you know the height at which the smoke is in your atmosphere. So since from the LiDAR, we're able to know, hey, at Lamont, Oklahoma, exactly these coordinates, we have smoke plume at, 5,250 meters. And we use that as our starting point, and then we can go back 96 hours. That is fairly accurate. The less information you have, even if you just kind of have like a rough estimate of where your smoke is, it kind of does start to fall out pretty quickly. But as long as you have reliable initial conditions, or at least to start running the backward trajectory from, it is pretty accurate.
All right. We'll encourage folks again to throw some questions in the chat. Otherwise, I'll throw another one at you, Kyle. This came to me now, so bear with me. In this work, was there any information that you wish you had that you didn't have access to? Data or what have you?
Yeah, I would say probably, I wish probably the incorporation of more AERONET sites to probe kind of how the physical properties are changing. And there certainly are more than are used here. So my work was kind of a companion or coming off of another student's master's thesis in our group. And so some of those had been selected kind of before I got in there based on predefined criteria. And I'd sort of inherited that and using a lot of the same AERONET sites. Although in the future, I would like to incorporate more of those direct kind of ground-based sensing of our aerosols so that I kind of just get more information on how our aerosols are evolving in the atmosphere. And, you know, kind of better answer questions about if some of that larger material is fallout and under what conditions it does.
Okay. Hey, Jordan Girth, I see you have a question.
Yes, I do. Kyle, thanks for your presentation. Quick question with regards to some of the services that NWS provides. One of the things that we notice is that when smoke is transported far away from the original fire, and especially varying based on the time of day, we can get, well, we are aware that local 911 centers get inundated with calls just because people smell smoke, not because they see fire. Do you have any guidance for how we can track smoke specifically that people can smell and have a prototypical model of how what times of day people are more likely to smell smoke in low concentrations?
Ooh, that's an interesting question. So yeah, I mean, I guess if you're asking specifically about kind of some of those more like long range smoke transport, so I guess you're smelling it, it's likely to have become suspended in the boundary layer, close to the atmosphere or close to the surface. That would make sense. So as far as estimating when it would arrive, so I would imagine, especially when you have those long range smoke events, you do have sometimes, you know there's a fire, you know it's arriving, or know that it's, at least there's a chance that it will. I would encourage, or at least experiment with trying to maybe do forward trajectories from HYSPLIT to estimate the height at which that will arrive and how long it will take that smoke plume to arrive at your site. As far as time of day, I can't really think of any application of this research to kind of understanding, you know, if someone's more likely to smell it or you know, call 911, you know, if it's at 6 a.m. or 6 p.m. But as far as just the time and when it'll get, I would kind of recommend experimenting with, you know, HYSPLIT style scheme, except forward trajectories this time.
All right, thank you so much.
Alexa Ross has a question. What are the implications of your findings for public health and at-ground air quality? For example, do you think a smaller smoke aerosol size would have more adverse effects on public health compared to larger sizes?
Yeah. So we know that you know, some of those smaller aerosols do tend to be a little more dangerous just because of, you know, how they're able to enter your respiratory system and kind of become lodged in the lungs and cause other health impacts. And so I would say that's definitely smaller smoke or just really smaller particulate matter sizes do tend to be more dangerous than your much larger aerosols. You know, I will say that in this research, we definitely do observe kind of slightly smaller aerosol. Next slide, maybe. Yeah, slightly smaller aerosols with time. I will say that that is not significant. It's certainly detectable in the data. I'm not sure that it's so significant as to where smoke that arrives, you know, in 2 days is quantifiably less dangerous than smoke that arrives in 4. But generally speaking, yes, smaller smoke aerosols do have more adverse public health effects than the larger ones.
I think we would need more AERONET sites to help discern that question. I'm not being facetious either. I know it sounds like I am based on your earlier answer, but give everybody just one more moment to get that last burning question into the chat or indicate you'd like to ask. It doesn't look like we have any more. So I believe that concludes our discussion, and I can turn it back to Jordan for his final remarks.
Thank you so much, Chris. I'm not sure if that was a pun about the burning questions at the end, but we seem to have extinguished the discussion. Anyways, Satellite Book Club is going to be continuing next week, March 21st. We got Frank Alsheimer, Science and Operations Officer from Columbia, and Tim Schmidt from NESDA STAR providing an update on the GXS instrument for GeoXO. We're still probably about 10 years away, but it's always time to get ready. In the meantime, if you have any questions for our Tower S team, please contact Ashad Bowman or Emily Maddox. Email addresses are there on the screen. Always happy to support anything related to satellite. Tower S channel on the NWS internal Slack workspace is also an option if you are interested in communicating with us that way. We're typically available during standard Monday through Friday working hours. With that, once again, I'd like to thank Kyle so much. We have such a range of presenters. Really appreciate you taking time from your schedule as a student, no less. Excellent research. And once again, thank you so much, Chris, for serving as our facilitator today, and for all of you for being with us. And with that, we will wrap it up there. I will be on spring break next week, but I hope you'll join us, and I'll catch the recording. Until then, take care.